Okay, so now you've been told that when you see a differential equation, a first-order differential equation take on this form, or if you can rearrange things using algebra to put it into this form, then it's called a linear differential equation. But I promise to tell you what is really meant by linear here, and this is not going to be too important to understand fully now, but it will be when we get to second-order differential equations. So whatever you can understand about it now will pay off later on. So I'm going to start by relating this word linear to what you learned about in linear algebra. So there's a reason Math 4a is a prerequisite to Math 4b. So here's a summary of some of the things you learned in linear algebra. So you learn about these linear systems, right? Where you've got this known matrix of coefficients, and you've got a known vector here, and you've got this unknown thing that you're solving for. And you're trying to find a vector here so that when you apply the matrix to it, you get the output here. And a solution is just a vector so that when you substitute it in here, this ends up being true. So these are called linear systems in linear algebra. And you want to solve, meaning you want x. But this isn't just like, middle school algebra where they're just like, find x, and then you have to find a number, right? Here, you're interested in finding all possible solutions. And sometimes there are many. And sometimes the set of solutions is a space, a vector space with some dimension, and then you want to describe it using a basis. So there's all this linear algebra theory that goes into just figuring out what it means to solve for x in this context. Well, here's something you can do. This is something you learn about in Math 4a, so I'm just kind of reviewing it. What you can do is first look at a homogeneous linear system. First, remove b from the picture. Remove b and look at homogeneous. A homogeneous linear system is one where the right-hand side is 0. Now, find all solutions to this one. So there are some set methods for finding solutions to this. And so you have methods for doing it. So find all solutions. In other words, find the general solution to a homogeneous linear system. Let me separate this a bit. So the goal I'm still talking about the goal of solving ax equals b, finding vectors x such that ax equals b, but I'm saying a strategy is to first remove the b from the picture and just solve ax equals 0, then find all solutions. Then, say you have a solution, let's call it x of h, is a solution to this one, to the homogeneous linear system. So I'm saying x of h because it's a solution to the homogeneous system. So what I mean by that is ax of h is 0. Then, here's the next thing you should do. Find just one solution to the non-homogeneous, the original linear system. Find one solution. Let's call it x sub p. For a particular. Find one particular solution to ax equals b. So that means we have a x sub p equals b. Then, here's the kind of magic that happens, or just linear algebra that happens. It's pretty plain, I guess. Then if you apply a to any solution here, x of h, to ax equals 0, let me write that better, plus the one particular solution you found, so this is the particular solution you found, then you can use linearity. Linearity means the action of the matrix on these vectors distributes over the addition. And when you do this, you get, for this term, you get 0, the 0 vector, and for this term, you get b, right? Because x sub h was just some solution to the homogeneous linear system, ax equals 0, and x sub p was a solution to ax equals b. And so overall, you get b. So look at what we have overall. A times this vector equals b. So here's what we are observing, and this is something you probably saw in linear algebra, although not everybody quite gets it the first time. So what we're observing is that given any solution x sub h to ax equals 0, the homogeneous system, and a solution x sub p to ax equals b, we have that x sub h plus x sub p is a solution to the original non-homogeneous linear system, ax equals b. So if you can find all possible solutions to the homogeneous linear system, all possible x sub h's, and just one x sub p, then you can just add your x sub p to the x sub h's and generate all possible solutions to the non-homogeneous linear system. Now, this is an idea that we'll use repeatedly in the course, especially when we get to second-order differential equations. All the theory that you see here is powered by one really, really important fact. So what made this work, this trick that you can work with a homogeneous linear system, find the general solution to it, and then find just one solution to the non-homogeneous system. What made this all work is this fact here. The fact that the A here distributes over this addition. This is called linearity. So the property of matrix action on vectors, which states that the matrix will distribute over vector sums and scalings, that is called linearity. We say matrix action is linear here. So wherever in nature or in mathematics we find this phenomenon, linearity, we can apply this theory. We can apply this idea about, if you have a thing that's acting linearly, like a matrix here, then you can talk about linear systems, and you can talk about solving them by solving the homogeneous one in general, and then finding a particular solution to the non-homogeneous, and then adding. Okay, so the reason I'm saying all this is that in differential equations, you do find an example of this, but it's not a matrix. It's a different kind of linear operator. So let me write down the form of the kind of thing that we're referring to as a linear differential equation. It's something like this, right? Anything you can write into this form. Let me write it actually, instead of writing x prime, let me write dx dt. Now, here's another way of writing it. So I want you to think of, let me write this d dt a little bit differently. When I write dx dt, the way to think about that is that x is a function, and d dt is a derivative operator that's getting applied to the function. So on the left-hand side, here I have a derivative operator getting applied to the function. So this is an operator that does something to this function. And then for this other term, I have a function of t getting multiplied by the function, which you can also think of it as doing something to it, multiplying it by a certain function of t. And then here, I've rewritten it so that you see this overall operator acting upon x. So it's as though you've got this action, this thing that does stuff to functions, doing stuff to x, and then what comes out as the output is q of t. This is a linear operator. That's what makes this a linear differential equation. So let's call this L. So I'm going to call this fancy L for linear operator rather than A. Although I could call it A, it's just A might make you think of matrix. But you should think it's actually pretty similar to a matrix. So L x equals Q. This is our differential equation then. If I just define that L is d dt operator plus the multiply by p of t operator. So if I just define this, then our differential equation is simply that. And you can think of functions as vectors. So back here, when I was looking at the Math 4a linear algebra style linear systems, it was matrix on vector equals vector. Here, it's linear operator, which is like a matrix, on function, which is like a vector, equals function, which is like a vector. So, you should not yet be convinced that this is linear. This is something we need to check. So, let's do that. So here's the definition of L. And the vectors in this picture are functions. So if I'm going to apply it to a sum of vectors, I need to apply it to a sum of functions, like maybe x of t and y of t, something like that, two functions of t. So that's what L applies to. Here I'm leaving out the of t, but I could put it there. So let's see. And actually, for the full picture, to see what linear means, or to check that L is linear, I need to not just apply it to a sum, but to a linear combination. So something like c1 x of t plus c2 y of t, maybe. Apply L like that. So if I use the definition of L, then this would be d dt plus p of t applied to c1 x of t plus c2 y of t, which is d dt of c1 x of t plus c2 y of t plus p of t times c1 x of t plus c2 y of t. And the derivative distributes. The derivative is linear, so I can totally do this. Let me just write x prime of t plus c2 y prime of t, just to not write as much. And then here, multiplying by p of t, that totally distributes as well. P of t x of t plus c2 p of t y of t. And now I can join these two terms, sort of group them together, and group these two together. And the red grouping together, if I look at that, that's d dt plus p of t applied to, actually I want to pull out the c1. c1 times d dt plus p of t applied to x of t. And then the blue grouping is c2 d dt plus p of t applied to y of t. And so overall, what I have is c1 L of x of t this is what L is. This here is L of x of t, right? That's how L operates, plus C2 L of y of t. And so from start to finish, so right now my face is kind of covering things up. From start to finish here, we go from L of a linear combination equals the linear combination of the L's applied to the individual vectors, where the vectors here are the functions. So this is linearity. It's just like how if you take a matrix and apply it to a linear combination of two vectors, c1x plus c2y, then you're going to get a linear combination where the matrix is applied to the vectors individually. That is linearity. So what we're observing back here is the linearity of L, where L is this specific operator. That's what makes these differential equations linear. When you can write a differential equation in this form here, it's linear because it's something you can write as a linear system. And this is a linear system because the L showing up here is a linear operator. So that allows you to apply all of the theory that we just went through from linear algebra. For example, if you have a solution to L x of t equals the 0 vector, which is the 0 function, and a solution to this non-homogeneous linear system, so say this one x sub h and this one x sub p, then when you apply L to the sum, then you should find that the sum is a solution to the non-homogeneous linear system. Finally, let me give you an example of a differential equation that would definitely not be linear. So say I gave you x prime plus x squared equals t. This would not be linear, and look what happens if I define the left hand. So one way to see that it's not linear using our sort of simplistic definition, which only applies to a specific case, is you cannot write it into this form. There's no way to rearrange things so that it looks like x prime plus function of tx equals function of t. And this is a perfectly good definition to use, and I mean, go ahead and use it. But I just want to show you that this also is not linear in the sense that the left-hand side is not a linear operator. So right now, the left-hand side would be d dt. The linear operator on the left-hand side would be d dt. Well, there's no nice way to write it, actually. What I'd have to do is write the way it operates on x of t is it takes the t derivative of x and then adds x squared. Here's one way to see that this is just not linear. So try applying it to a sum of two things, two functions, x of t and y of t. Then what would you get? You would get x prime plus y prime when you apply d dt to both of them, and then you would get x plus y squared, right? Now think about applying it to x and y individually and see what you get. So this one would give you x prime plus x squared, and this one would give you y prime plus y squared, which you could rearrange like this. Now, if L were linear, then these should match up. They should agree. This should be the same as this. Well, this part matches up, but is this the same as this? Definitely not, right? And you can see exactly by how much it's off. This will have some cross terms when you square this out. So this is not a linear differential equation, and that's the reason why. So all that linear algebra theory would not apply to this situation.